All right, so what I'd like to do here is, in some sense, similar to the last video. I'd like to take a look at the ratio test, not as much from what the ratio test is, but more from the perspective of when to use the ratio test. Because we know what the ratio test is. If you're given a series, you take a limit as n goes to infinity of the absolute value of a term raised to the 1 over n power, and should that root, note this is like the nth root of absolute value of a to the n, should that root evaluate to something less than 1, you get a convergent series, because your series will essentially be acting like a convergent geometric series. Should this limit be greater than 1, you get divergence, because your series is acting like a divergent geometric series, in particular a geometric series with common ratio greater than 1. Should you get the equal to 1 case, unfortunately the root test is inconclusive. We saw an example of that last time. We saw a series whose root test evaluated to 1 for a convergent series and for a divergent series. Well, unfortunately nothing can be said there. Right, so this is what the root test is. And then the question becomes, well, when can we use the root test? Well, a couple cases that work nicely with the root test are when you have something of the form r to the n. That's going to work really nice with the root test, because when you take the absolute value of r to the n to the 1 over n power, power raised to a power, cancel out the exponents, and you'll just get absolute value of r. That works quite nicely. And another thing that works quite nicely is if you have an expression that may be more complicated than r that's being raised to the nth power. So in this case, this expression that's more complicated than just r, well, still, if it's being raised to the nth power, you take a power raised to a power when you raise to the 1 over n power, and n times 1 over n is 1, so ultimately you just get out what was inside your original parenthesis, but with respect to absolute values. Something else I'd like us to recall, just so that we're on the same page, this is something that we saw whenever we were working out a couple root test examples. In fact, when we were working out those inconclusive examples related to the root test, we saw this fact from Calc 1, which is that when you have n raised to the 1 over n power, you get 1. And again, the cheap way to remember this is if you think of n going to infinity, you can think of the exponent going to 0. And, well, the exponent going to 0 means that the expression is essentially going to a number raised to the 0 power, which is 1. That's a cheap way to remember it. There is more justification on a previous slide of a previous video. Right, so what I'd like to do here is address two examples that are related to the root test so that we can see the root test sort of in action. And the first example is an example that involves a factor of r to the n. In fact, if you watched the ratio test video previously, we actually, forgive me for shuffling this around as much as I just did, we actually saw this exact same series using the ratio test. The sum 2 to the n over n, and what we saw was that the series started acting like a geometric series with common ratio of 2. And so, well, here we're dealing with the exact same series, so we should get the exact same result, but let's just make sure that that's the case. So, to do the root test, what do? We take each term, absolute value, and raise it to the 1 over n power. Just so we're all on the same page here as to why we call this the root test. I haven't explicitly written this yet on this slide. Remember, the nth root of any number is just the 1 over n power. So, well, if we write as the 1 over n power, we're sort of saving ourselves a step from writing out the root test, although the root test certainly involves a root because, well, the power 1 over n is in fact an indicator of a root being present. Okay, that being said, let's actually work through the details of this. So to work all this out, we plug in what our term is. Our term of our series is just of the form 2 to the n over n. And what we do is we raise that to the 1 over n power. This is a fraction which works beautiful with exponents. You just take the exponent and apply it to the top and to the bottom. Well, to the top, the n and the 1 over n multiply to be just 1. So here we have like 2 to the 1 in effect. And then downstairs we have n to the 1 over n power. But we're taking a limit here. So when you take a limit of n to the 1 over n power, this is leveraging that old Calc 1 fact. And what that turns out to be a 1 downstairs, we get the 2 upstairs, and we get a 2 out as a result. Note, this is the exact same result we got out with the ratio test. The ratio test told us that this series eventually starts acting like a geometric series with common ratio 2. and the root test also told us that this series starts acting like a geometric series with common ratio 2. Well, regardless of the root test or the ratio test, we see now that our series diverges since the ratio test yielded 2. And specifically, 2 is bigger than 1, and that's what's causing us the issue with the divergence. I mean, it's not really an issue, it's just good to know, but an issue in the sense that the sum of the terms of this series does not add to be a number on the number line. If you took this series and added up its terms, you would end up with an infinite value. Okay, so that was a nice example that was similar to one that we saw previously. And now how about one that's different from what we saw previously? Here we have sort of a more complicated expression, but it's still being raised to the nth power. So this is sort of the form that we were talking about above. What if you don't just have a constant raised to the nth power, but something more complicated? Well, that's perfectly fine. The root test actually works very nicely here, because if you take the expression for each term and you raise it to the 1 over n power, that nth power and the 1 over n power are going to work really beautifully together. So in particular, when you write this out and you plug in what the an terms look like, you get this whole thing in parentheses, raised to the nth power, raised to the 1 over n power. Well, a power raised to a power, we multiply the exponents, and ultimately n times 1 over n is just 1. So now down below, our power is 1. We still have the absolute values to contest with, but so be it. Whenever we look at what's inside, looking at our individual terms, note we have an equal heavy rational expression with degree 2 upstairs, degree 2 downstairs. So when we take the limit as n goes to infinity, we merely pluck off the leading coefficients of 3 and 2. So here we now get the result that the series which we're looking at begins eventually acting like a geometric series with common ratio 3/2. Well, if the common ratio in your geometric series is 3/2, that's bigger than 1, you're definitely going to diverge, and here we diverge as well. So since 3/2 is greater than 1, we can say that our series diverges since the root test, oh, I said ratio above, didn't I? Whoops. Since the root test yielded 3/2. And 3/2 is greater than 1, and as a result of our root test yielding a value of greater than 1, we are in the case where our series diverges. And right, just to recapitulate what we've discussed to this point, when it comes to the root test and knowing when to apply it, be on the lookout for expressions of the form a constant to the nth power. Those are expressions that work fairly nicely with the root test. And even better, when you have a large collection of elements raised to the nth power, then that's going to be something that works especially nice with the root test. And the final remark is that Calc 1 fact. Remember that when you have n raised to the 1 over n power, and you take the limit as n goes to infinity, remember that that goes to 1. That can be especially useful in some root test scenarios.